Okay, so let's go ahead and take a look at notes 2.5. The first three theorems we're going to talk about, this is a little bit of a review, so pause the video and go ahead and read about those first three theorems. Go ahead and do that now, please. Okay, now what I'd like you to do is take a look at the next three theorems. For example, we have every polynomial with real coefficients can be written as a product of linear factors and irreducible quadratic factors with real coefficients. So, for example, if you have a cubic polynomial and you have two imaginary zeros, let's say I and negative I and a real zero, let's just say x equals 0. Notice that when you multiply this, notice you have x times the quantity x squared plus 1. So again, real coefficients. What about this next theorem this is pretty cool. Again, every polynomial function of odd degree with real coefficients has at least one real zero. That makes sense. Look at the end behavior. So you're going to cross the x-axis at least once. And we have complex conjugate zero. So suppose that f of x is a polynomial function with real coefficients. Notice that we have a plus bi and a minus bi. So let's do this example. Let's say you have an imaginary zero at I and a real zero at 3. Notice that when I go ahead and multiply this, I have non-real coefficients. So again, complex zeros come in pairs only when the coefficients are real. So for this first example, I'm going to show you how to do something two different ways. So for example, let's say you have x equals 2i and negative I. Those are your zeros. So you can write x minus 2i and x plus 2i. Now, if you go ahead and expand, I squared is negative 1, so we end up with x squared, y equals x squared plus 4. But here's something else I wanted you to think about. Let's say that you wanted to do it a different way, okay? Let's go ahead and put that one on hold for a second and think of a different example. Okay, so a completely different example over here. Let's say that we have zeros at 3 and negative 4. So wouldn't your equation look like this, x squared plus x minus 12? Now, do you think it's a coincidence that this number is the product of these two solutions? So if this is solution 1 and this is solution 2, notice that the constant is solution 1 times solution 2. And notice that the middle term is the opposite of the sum of the two solutions. So we could that's how it works every time. So what we could do over here, if we know that solution 1 was 2i and solution 2 was the opposite of 2i, you could have said, well, this is the opposite of 2i plus negative 2i. And over here, this was 2i times negative 2i. So you would end up with y equals x squared minus 4i squared, which is x squared plus 4. So it's just another way to think of it. Okay, so let's go ahead and take a look at the next example. This time you're going to write an equation of a quartic with real coefficients with zeros, x equals 1 minus I and 2 plus I. So first of all, if it's quartic, it has 4 zeros. It's fourth degree. And notice it has real coefficients, so you know that 1 plus I and 2 minus I must also be zeros. So go ahead and write your skeleton equation here with an A and see if you can go ahead and make a plan for finding the value of A. Go ahead and pause the video, please. Okay, so hopefully you have the first step. And now we're not going to leave i's in the equation. Okay, so what we're going to do is you have a choice. You can either multiply these, or you could use that method that I showed you earlier. It's up to you. I wanted to actually show you one more method to kind of make this a quick way to multiply this out. If you have x minus 2 plus I, because again, distribute your negative sign, x minus 2 minus I, distribute the negative sign, you want to multiply those together. Again, if you did x times x, and x times negative 2, and x times negative I, and then the negative 2, and then we'd be here a while. You could also do something, I don't know, I like to call multiply by grouping, where you could group these terms together. So notice you could do first terms. the inside and the outside terms will cancel out because I times x minus the quantity x minus 2 and negative I times the quantity x minus 2 cancels out. So we have minus I squared. So that's just one other way that you could multiply those out a little bit more quickly. Okay, so for this one, I think I'm going to use the method that I showed you earlier, where this number is the opposite of the sum of the solutions. So that would be a negative 2. And this number is the product. This number would be 2. So go ahead and pause the video and just check the work and see if that is correct. All right. So we have y equals a times x squared minus 2x plus 2. And again, if we expand over here, we have x squared minus 4x plus 4 minus I squared, which is plus 1. So here is our polynomial. Now, again, this is a unique answer because they did give us a point, 0, 20. So let's temporarily put 20 in for y and 0 in for x. Go ahead and find a. Go ahead and pause the video and write an equation. All right, so we went ahead and found a is 2, and so there you go. Now again, they want you to write this equation with as linear factors, so we don't want to leave any i's in the expansion here. Okay, let's go ahead and take a look at number 3. So for number 3, you are trying to find all zeros. So the first thing we're going to do is write the possible rational zeros. So go ahead and pause the video and write down if there are rational zeros, what would they be? Okay, so if we had a calculator for this one, and again, we could do this one without a calculator, it would just maybe take some time, okay, because it ends up that the rational zeros are at negative 2 and 1/3. Okay, so again, the calculator does help, but again, without the calculator, we could eventually find, there we go. Again, it would have taken a while, but we could have found all the zeros. But again, let's go ahead and start with a negative 2, pause the video, and when you're done, go ahead and synthetically divide out the 1/3. All right, so we know that there were zeros. X equals negative 2, x equals 1/3, so we're left with 3x squared plus 3x plus 3 equals 0. If we could divide everything by 3. And we're not able to factor this, so we need the quadratic formula. So go ahead and pause the video and find the other two zeros using the quadratic formula. Go ahead and pause the video now. So we ended up with x equals negative 2 and x equals 1/3 as our rational zeros, and then we had some complex zeros, negative 1 plus or minus I root 3 over 2. All right, so again, if you notice, we started with a 4th degree, and we needed to whittle that down to a quadratic so that we could either factor or use the quadratic formula to find the last two zeros. Okay, let's go ahead and take a look at the next problem. Go ahead and think about a plan. What would you do to start this problem to find all the zeros? Okay, so we'll use synthetic division with 1 plus 2i. So we have 1 plus 2i. Go ahead and combine like terms. So we have negative 1 plus 2i. And let's see, we'll multiply 1 plus 2i times negative 1 plus 2i. And we end up with negative 5. And then we have 1 plus 2i, again, combine like terms. And we have 1 plus 2i times negative 1 plus 2i again. We already figured out what that is. That was negative 5. So we did end up showing that that was a 0. So now we're going to go ahead and pause the video and synthetically divide the 1 minus 2i. We'll be left with the quadratic. And again, 1 minus 2i was also a 0. You're left with x squared plus 1, which we can factor. So our zeros are 1 plus or minus 2i and plus or minus I. So it says find all zeros and factor into linear factors. Well, we could write this as x minus I times x plus I times x minus 1 plus 2i and x minus 1 minus 2i. But again, we're not going to leave the imaginary numbers, so we're going to expand. We know this was x squared plus 1. So again, use the method of your choice to multiply those two quantities. Okay, so we found our zeros. And then again, I decided to take the opposite of the sum of the solutions for the middle term and multiply the solutions for the constant. There we go. Okay, so let's go ahead and try number 5. I'm going to ask you a sketch a graph. Go ahead and use your knowledge of end behavior and zeros and multiplicities, and go ahead and sketch a graph. Pause the video, please. Okay, so first we want to find our end behavior. If we multiply this out, we have x to the 5th, right? A lot of other terms in there, but basically we know that the degree is 5, so the arrows will, the end behavior will look like this. The arrows are going in opposite directions. Notice that we have a 0 at 0 with multiplicity 1, at -5 with multiplicity 2. So we're going to bounce when we get to the -5, and we're going to pass when we get to the 0. Now, notice that we can't see imaginary zeros. Now, if you graph this on your calculator, you might have a change in direction in there somewhere that implies, we might have some imaginary zeros. However, this is just a sketch, so that just looks fine to me. Nice job on that. Let's go ahead and try number 6 now. So go ahead and pause the video for number 6 and see if you can sketch a graph for A through D, again, if possible. Okay, so let's take a look at A. So distinct real zeros, that's the same thing as saying x-intercepts. And so again, if the degree is an odd degree, there's no way that you're not going to have at least one real zero. You can't have 0 x-intercepts, and that with that particular end behavior. Notice part B, 2 distinct real zeros. You could have 2 x-intercepts for a 5th degree. You could have 3 x-intercepts. Now this one's interesting. Notice you won't have 4 real zeros because you have a total of 5 zeros. And remember, the complex zeros where the B, A and B are real numbers, where B is not 0, so it has an imaginary part to it. Notice that those complex would come in pairs. They would have the complex conjugate because, again, we're saying real coefficients. So D is not possible. Let's take a look at number 7. So what does it mean to have non-real coefficients? Go ahead and pause the video and see if you can answer the questions A, B, C, and D. Go ahead and investigate, and then turn the video on after you've done that. Okay, so let's investigate a little further. So notice that there are non-real coefficients, and we know that complex zeros, A plus BI, where A and B are real numbers, and B is not at 0. So in other words, there is an imaginary part to this complex number. Notice that only when all of the coefficients are real, that's when they come in pairs. So there you go. So they come in conjugate pairs only when all of the coefficients are real. So you might think, oh, well, Mrs. Corbis just said that I is 0. So does that mean that negative I must not be a 0? Well, if you go ahead and use synthetic division, look at this. I have a remainder of 0. So far we have x and equals I and x equals negative I. But again, if you take a look at this one, I will show you that you could also use synthetic division, and it ends up that for this one, I had multiplicity 2. So again, there was an I without a conjugate pair. So here were the zeros for that one. But again, that's just one way that you could end up with non-real coefficients. So go ahead and pause the video and try problem number 8. So we know that it has real coefficients, so if 2 minus I is a 0, 2 plus I is also a 0. So we need to find A, but why don't you first go ahead and use the method of your choice to multiply x minus the quantity 2 minus I and x minus the solution of 2 plus I. Okay, so now we could use the fact that x 0, 2 is an ordered pair, a solution to this equation, so we can temporarily put 2 in for y and 0 in for x, and find out that A is 1/5. Okay, so for number 9, we are going to find all 3 cube roots. So again, we know that it's x cubed plus 8 equals 0. There are 3 zeros. Now, I think we know that one of them is -2, because -2 cubed is -8. So go ahead and use synthetic division and see if we could find the other 2. Did you remember to use a placeholder for the x squared and the x term? So now we could use go ahead and use quadratic formula and find the other 2 zeros. So using the quadratic formula, we get 1 plus or minus I root 3, and we already had the -2, so we have 3 zeros, 2 -2, a real 0, and then we have 2 complex zeros with the imaginary part. B is not equal to 0. It had the imaginary part there. Okay, so why don't you go ahead, for the last part of the notes here, go ahead and pause the video and see if you can sketch a graph for 10A and B. So for number 10, I feel like I'm misspeaking there. I shouldn't say imaginary. I should say two complex zeros of the form a plus bi, where a and b are real and the b is not equal to 0. So it has an imaginary part. Because again, the zeros, the complex zeros, might be something like 2 plus or minus I, something like that. Which technically, you would call that a complex number. So notice this graph would work because we have one real 0, and again, you can't see imaginary zeros, but there certainly could be, or actually we can see complex zeros with the imaginary part not equal to 0. But again, that graph would work. Let's go ahead and do B together. Notice you have a negative y-intercept, exactly 2 negative x-intercepts, 1 non-negative x-intercept, and a negative leading coefficient, which tells you the end behavior looks like this. So go ahead and pause the video and see if you could sketch this graph. And there you go. Okay, so great job, everybody. Those were notes for section 2.5.